Good day and welcome to part one of our discussion on differentiating logarithmic functions. And we're going to just jump right into it. That is, can we somehow come up with a formula to represent the derivative of the natural log? And recall, typically, when we are trying to come up with a new differentiation formula, we have to go back to the definition of the derivative. But it turns out that in this case, because we know the inverse of the natural log, the exponential function, and we know how to differentiate the exponential function, we can utilize both that inverse function and implicit differentiation to differentiate the natural log of x. And this will be a very useful technique that we utilize several times in our upcoming discussions. And our starting point is this expression y equals the natural log of x. Recall that the inverse of the natural log is the exponential. What that tells us is if we apply the exponential function to each side, on the right-hand side, the exponential of a natural log simply gives us back x, and on the left-hand side, we have an e to the y. Our goal at this point is to somehow find dy dx. And note, we can do so using a technique from Calculus 1. We will differentiate this equation implicitly. And in order to differentiate implicitly, we will differentiate both sides with respect to x. On the right-hand side, we have an explicit derivative. The derivative of x with respect to x is simply 1. On the left-hand side, this is where we have the implicit derivative. We have y, and we're differentiating it with respect to x. Now recall the rule of thumb with implicit differentiation. You differentiate exactly how you want to. That is, in this case, with respect to y. So the derivative of e to the y should simply be e to the y. But because it's an implicit derivative, we must multiply by dy dx. And that is the key step to this problem, because we can easily now isolate for this quantity we want to solve for, dy dx. It is 1 over e to the y. But recall, we want to write this in terms of x, and if we look above, specifically at our second line before we differentiate it, e to the y is simply x. So this is 1 over x. And believe it or not, that does it for us. What we have found is that the derivative of the natural log of x is 1 over x. And just to reiterate, this technique of rewriting with the inverse function and differentiating implicitly is something that we will encounter in upcoming sections. So it's worth taking some time to make sure you understand the basic argument that we have used. Now this does lead to a natural question. Remember, corresponding to every rule of differentiation, there is a rule of anti-differentiation. That is to say, we should have a corresponding indefinite integral. So what I want to ask you is, what is the antiderivative of 1 over x equal to? So I would like you to pause the video for a moment and write down on your note sheet or a piece of paper what the value is for this antiderivative. Now, the common response that I get is the natural log of x plus c. And I'm going to note that's not entirely correct, at least not in this current form. There's one small subtlety we have to worry about, and that is matching up domains. What values of x are we talking about? This function 1 over x is defined whenever x is not equal to 0. Whereas the natural log of x requires x to be strictly positive. So notice the subtle difference. On the left, we could have negative inputs for x, whereas that is not allowed on the right. And it turns out that we can very quickly and simply take care of this. And all that is required is that we add absolute values. So let me go ahead and just summarize this with a few observations. So a key new anti-differentiation formula. The antiderivative of 1 over x is the natural log of the absolute value of x plus c. And that absolute values around the x are of the utmost importance. And this is something that we should be extremely excited about because we've filled in a major gap that we've had ever since Calculus 1. And that gap that we've had since Calculus 1 is, recall this very common antiderivative formula that undoes the power rule of differentiation. The antiderivative of x to the n is 1 over n plus 1 x to the n plus 1 plus c. And remember, there's always been a small caveat that goes with this, as long as n is not equal to minus 1. And it turns out we no longer need to worry about the case when n is equal to minus 1. N equals minus 1 has now been taken care of for us. So let's finish up by taking a derivative. Similar to what we've done in our previous section with differentiating the exponential functions, once we have these new formulas, it's an opportune time for us to practice our differentiation and integration skills for several big reasons. One, because it's important to remind ourselves of all of these important Calculus 1 concepts so that we are very quick and efficient with them when we need them throughout this semester. And also to get us ready for what is to come, the remainder of this semester, which is going to involve quite a bit of integration. So to summarize the two new formulas we've introduced, the derivative of the natural log of x is 1 over x. The antiderivative of 1 over x is the natural log absolute value of x plus c. So for example, if we'd like to differentiate the natural log of cosine x, we would need to use the chain rule. We have an outside function natural log, an inside function cosine. So the chain rule of differentiation tells us we differentiate the outside function, 1 over, we evaluate it at the inside function cosine, and then we multiply it by the derivative of that inside function. And the derivative of cosine is minus sine. So we're left with minus sine over cosine, which we can leave as is, or we could certainly express this as minus the tangent function. Let me finish by noting, a generalization of this. It is very reasonable to encounter the derivative of the natural log of a function. And in general, we would differentiate this using the chain rule. We take the derivative of the outside function, 1 over, we evaluate it at the inside function, and then we multiply by the derivative of the inside function. And note, there's nothing to memorize. It's just making sure that we understand that we're using the chain rule. So that finishes up our current discussion. In the next video, we will continue on practicing more examples. Specifically, we will be evaluating some integrals that we were previously unable to handle. So stay tuned and take care.